Okay, so now we're gonna go ahead and do the second part B of this worksheet. And it's basically saying what is the starting materials if you want to make synthesize the ether that they give you. So this is what they give you, and you need the starting materials. So there's you got to think of I guess you could see that there's two ways of synthesizing this ether, right? So the first way would be to use um, this way right here, where we use an alkoxide that is on a propane cyclopropane chain, right? And yeah, and we're gonna mix that with some, I guess, let's just use iodine as our leaving group. So it would be iodopropane or 1-iodopropane, or you can say propyl iodide, one of those two, right? But we have our alkyl halide leaving group and our alkoxide, which is going to attack via an SN2 mechanism, giving us this product, right? So, or you could have said that this is your starting material, where we use a really good leaving group. You can use iodine, bromine. I would stick with those two just because chlorine isn't as good of a leaving group as bromine and iodine. So when it comes to the halides, okay? Let's see what else we have. And we would need to react that with an alkoxide. In this case, ours would be some sort of propoxide type of thing, with a 3-carbon chain with the O minus at the end. All right, which one of these ways is better? I'll give you a second to think about that. 1 second is passed, and here we go. So the one that I would say is the best bet is the first one here. Now you say why? So I would argue that since we have a primary alkyl halide here and a strong nucleophile, this primarily will go SN2, right? And that SN2 mechanism it'll only produce this. Okay, you'll have very little E2 competing with this, just because E2 mechanisms prefer tertiary alkyl halides, then secondary, and lastly primary. Okay, so but this one on the other hand, we have a secondary alkyl halide. So this reaction would actually be competing with an E2 reaction, and the product would look something like this. Okay, where this H is deprotonated to form that in an E2 mechanism to form this product here. So the better choice between your substituents, or not substituents, your starting materials is these two here, just because you eliminate the competing E2 mechanism. It can occur. I'm not saying it can't occur. We do know that primaries, alkyl halides can go E2, but they're more likely to go SN2. So that's why. So I would say the answer for those, for number one, or for letter A, oops. The answer for letter A is definitely, the best answer for letter A is this one here. For B, I'll give you a second. Okay, so these would be our starting materials. And let's just have a good leaving group. And then the O minus, all right? So you might say, okay, why didn't I put the O minus here and the I here? That's technically a correct answer, but a better answer is this one, because this one will primarily go SN2, giving you your ether as your primary product. Whereas if you put the alkyl halide on this one here, it would be competing with an E2 mechanism, okay? So same as the previous example where I explained here, it's better to have your alkyl halide on a primary carbon than it is to put it on a secondary carbon, because you eliminate other competing mechanisms. And that's a big thing in organic chemistry, right? So second one here, we would want to do something like this. And then our alkyl halide would go here. And we want our alkyl halides to be primary, just so that way we have primarily substitution. D would be something like this. And I'm switch it up. I'll just put bromine for why not. And that would be our starting materials there. For this one, I would definitely do, you can go either way actually, since they would both be primary. So you could do it like this. Let's see. You can react that with methoxide, where you have CH3O minus. And then don't forget about our benzene. Or you could do it the other way, where you have the alkoxide on benzene attached to the carbon on the benzene ring, like this, reacting that with a methyl bromide or methyl iodide, one of those two. So either one works. We'll do methyl iodide to stay consistent. So each of these work, right? And that's because both of these alkyl halides are primary alkyl halides, right? So they're going to mainly go SN2. And this one up here actually will only go SN2. And if it doesn't come to mind why, well, actually, they both only go SN2 now that I look at it. This one only goes SN2 because there's no beta hydrogen here. And again, this one only goes SN2 because in order for it to go E2, well, we know methyl halides don't go E2. Why? Because in order to form a carbon-carbon double bond, you need more than one carbon. And clearly, a methyl group only has one carbon, right? So you can't do it with, these both would work, is what I'm saying. So these both are perfect, either one. It would come down to the chemical engineer and which one of these reagents costs more or costs less to use as starting material. So let's see. This one here, we're adding well, we have a propane chain here, and then we have some tert-butyl group here. Clearly, we would want to put our alkyl halide on this primary carbon, so it would look something like this. So, or this is not tert-butyl, I'm sorry. This is, what is it? Isobutyl. That's embarrassing. And we would want to react that with this one here. And again, why? Because if we were to put the halide right here, the alkyl halide, we would have competing E2 mechanism, right? Since this is secondary, whereas this one's primary carbon. So it's only going to be, it's primarily going to go SN2 over E2, okay? Here we have an interesting looking one. So because this is tertiary, you would not want to put a alkyl halide on it. You would not want this to be your starting material. Why? Because this is tertiary. This, and then if you react this with a strong methoxide, this right here, these two right here would go what? Answer is E2, right? Because first of all, they can't go SN2, right? Because this is too sterically hindered to go SN2. And it's not going to go SN1 because we have a strong nucleophile here, right? But so the primary product for this one is going to be your E2 product, which is why you would want to change it up like this. You want to put your leaving group on the methyl group and then your alkoxide on that bulky group there. And that'll give you your SN2 mechanism here. Last one here for I would be, let's see, where would we want? I would want to put my, yeah, there's only one way you can do this. And I'll show you why. So you would have to put your alkyl bromide on, or alkyl halide. I'm going to do alkyl bromide in this case, on this portion of it, and not on the other portion, and I'll show you why. So this is the deprotonated version of phenol or phenol. So it's phenoxide, right? Why would we not want to put the alkyl halide here? So let me draw what that would look like. BR, oh, you may see it now, but we can't put it here because substitution reactions only occur on a sp3 hybridized carbon. This carbon right here is sp2 hybridized, right? So it would not go SN2 react. It would not undergo a substitution reaction. So you can't put your alkyl halide on this part right here for a Williamson ether synthesis. The only possible way is to have, your alkoxide be this phenoxide here, and then your alkyl bromide to be on this portion here. This would then go E2, or not E2, SN2, because this is primary. Oh, wait, no. This is actually secondary. Yeah. I might be tripping. That's secondary. I'm sorry. No, this is embarrassing. I'm pretty sure this is primary. Why am I blanking right now? Yeah, there's two hydrogens here. That's obviously primary. Okay, I'm sorry. So it's primary, therefore it's gonna go SN2 mainly over E2. Gosh, that was embarrassing. Why am I totally blanking like that? Okay, so that's the end of this video, and I'm sorry I totally had a massive brain fart over here on identifying a primary or secondary alkyl halide. I hope y'all cut me some slack for that. But yeah. Next part we'll go through is, how about we just go through 11B right now? There's no point in making a 2-minute video on it. So it's saying, show how you would make diethyl ether using ethanol as your only source of carbon and any other organic reagents. Okay. So you would need to have 2 reactions here, pretty much, is what I'm thinking. This first reaction of ethanol, we want to react it with a strong base, something, my go-to is always sodium hydride, right? And that is just going to deprotonate that. So let me redraw this portion here. So that negative charge, those electrons are going to remove that strong base to form our alkoxide here. And now we need to go form an alkyl halide that looks like this. But our starting material is ethanol. So what reagent would we want to use? Let's brainstorm. Okay, so we know alcohols undergo several reactions, right? If we want to do a substitution to make a good leaving group, we can use an HX, so over here on the left, HX such as HCl. So, well, we would want a better leaving group. So we would want to do something like HBr because the HCl is not as good of a leaving group. And we would want to do something like HI, even HI, right? So that would do an acid catalyzed substitution reaction. Or we can do something like using PBr3. I wouldn't want to use SOCl2 just because chlorine, again, is not as good of a leaving group as bromine or iodine, and that would not So we wouldn't want to put a chlorine here because our most efficient reaction would want a better leaving group. So something like bromine or iodide. So let's go ahead and use PBr3. That's an interesting. We'll show the mechanism for it. Okay. Okay. So what happens here for PBr3? Let me redraw this out a little bit better. Actually, I'll draw it down. So remember for this one, there's no pyridine required. So what happens here is that this oxygen has those lone pairs that are going to attack that. And if you attack that phosphorus, one of those bromines are going to leave, okay? So that's going to give us this OH, P, and then we'll do Br2, and we have a plus charge there. And what happens is this actually makes a really good, this is now a really good leaving group, and that is going to allow for bromine, this bromine that was kicked off over here, to come over and then do a backside attack on that, giving you the product, which we'll put up here. Br. All right, and now we're going to do a reaction between these two, and you would get your alkoxide attacking this primary carbon alkyl halide, and you would look something like that, like this. All right, so then you get diethyl ether. You could have also done this using a HX for your alcohol, so it would look that reaction mechanism would look something like this. OH, we can use HBr. That's going to attack that. That goes there. You get this. OH2. That's now a good leaving group. We know that we know primary carbon or primary alcohols when treated with HX are going to go S and 2 because you can't form a primary carbocation, right? So now your Br is going to come back here, come and hit it from the backside attack to form our alkyl halide. And then you would end up at this, once you get this, you would pop that back into this step and react it with the alkoxide generated from the first reaction. Okay. So yeah, those are the two methods of doing that. Either one works. But yeah, the next video for this thing will go over the predicting products of epoxide openings in base and acid. Alrighty, so there you go. I'll see you next time.